Once that's done, we'll see some visualized form of data analysis. We'll plot the histograms of the continuous numeric variables. And how do we do that? We'll use the matplotlib. So plt.histogram. So hist method from the matplotlib is going to be used in order to create this histogram. Histogram is just a visualized form to see the distribution of continuous data, and we'll have 10 beans. You can have as many number as you want. So we'll do it for a mileage. Okay, and there are two parameters. First one is the variable for which we want to create histograms, and the second is the number of beans. Okay, you can replace that with simply with 10, right? Instead of providing as a variable, we can simply hard code the scalar value as well. So we'll run this, and here is the histogram. It has got 10 bins, and this is the distribution of mileage. Okay, um, there can be several distribution, right? Distribution in the form of histogram is just a data distribution, and we are simply summarizing data with each bean. Okay, in summary statistic, we simply have just one bean, right? Which is centered around the mean, or centered around the median, or the the maximum or the minimum. But here we have 10 beans, so you have distribution at different section of the data, and that's much better to understand rather than the basic summary statistics. You can see that to the right you have, if you look at the cursor, there's some observation even at 50 and 60. Okay, and that's they are typically the extreme value. So we have fat tail, right? So fat tail is just a case when you have some observations very away from the other observations. So you can see my cursor, these small set of observations, maybe a few only, but they are totally different from the other set of observations. So they are extreme to the right. In statistics, we call them a typical case of a fat tail distribution, and we can remove them if we, if we're going ahead with any statistical analysis. We can overlay the probability density function also with respect to the histogram. So probability density function will ensure that we get it in percentage terms rather than the actual values. Here we have the actual values, right? The actual summarized value of mileage in each bean, right? For the first, and let's say we have 25, second we have 175, something like that. But here for PDFs or the probability density function, we would be having the percentage terms, right? And the area under that PDF is always going to be 1. So that's the constraint of a probability density function curve. And here is the PDF curve. You can see all of them are in percentage terms, right? It has to lie between 0 and 1, and it does lie between 0 and 1. If you take the area under this particular curve, you will get it as 1. As I was saying about the fat tail distribution, you can see the tail is quite longer in the right hand side of this curve, right? And we need to simply remove these extreme values, and then it will look somewhat normal, somewhat bell-shaped type. Okay, and that's what is an ideal data for data analysis. We'll do that for other continuous variables like length. For instance, yes, the distribution of length looks much better than mileage. There are hardly extreme values. There are hardly the distribution is hardly long-tailed. We can also have the probability density function for this. All right.